What is going on, guys? My name is Amos and I'm back again with another video. So in today's video we want to look at how we can decompose these two complicated rational fractions. Now I'm saying complicated because I'm looking at the denominator, right? So we want to see how we can decompose these two rational fractions. Now the denominator here is x squared plus x plus 1 raised to the power 2, and then here we have x squared plus 2x plus 2 raised to the power 5. Now this is going to take you a lot of time if you are going to apply the traditional methods. Now we want to see how we can use the Euclidean algorithm, right? We want to see how we can use the Euclidean algorithm to come up with this decomposition for both these rational fractions. Now this decomposition, we're looking for this decomposition in R, right, and not in C. Now that is just some added information there. We are looking for this decomposition in R and not in C. Now that is very, very important because the decomposition can be slightly different, especially when we have some terms or some denominator expressions that are not factorizable in R. We looked at that in the previous videos, right? Now first of all, we're going to start by calculating the discriminants of the two quadratic expressions that we have here. So just to know what we're dealing with, just to know what we're up against. So here the discriminant of the first one is going to be negative, because here b is 1, so b squared is that, and then minus 4a is 1 and c is 1, so we should get a discriminant that is negative, right? We have a discriminant that is negative, and then here what do we have? So here we have b squared is going to be 4, b squared is going to be 4, now minus 4, now a is 1, so minus 4 times 1 is 1, minus 4 multiplied by c, which is 2, is going to be minus 8. Now this is also going to be negative, like so. So the two discriminants are going to be negative. So already here we're getting the idea that these are not going to be factorized. The denominators are not factorizable, are not reducible in the polynomials. The two polynomials at the denominator are going to be irreducible in what? In R. And then we also have the squared here and the x squared plus 2x plus 2 raised to the power 5 here. So already we have many problems here. So what are we supposed to do? Now we're going to use our very good old friend, our best friend, that is going to be the Euclidean algorithm. Now we're going to now the technique is the same for both these rational fractions. So I'm going to allow myself to call this the first one f1. So this is going to be x to the power 3 minus x squared plus 2x minus 3, like so. Now this is going to be divided by x squared plus x plus 1. So what we're going to do is that, now this is never 0. In R, this is never 0. X squared plus x plus 1 is never 0 in R. So what we're going to do is that we're going to, use Euclidean division between these two polynomials. So we're going to divide, so here, we're just going to, separate, the rational fraction from, our overall solution. So what we want to do is to try and decompose, try and perform, the Euclidean division between the polynomials. So between x to the power 3 minus x squared plus 2x minus 3 and x squared plus x plus 1, like so. So this is what we want to we want to divide x squared. We want to divide x to the power 3 minus x squared plus 2x minus 3 by x squared plus x plus 1. Now here we're going to get this first term here, and then we're going to divide it by the first term here. So here when we divide it by the first term, here we're going to get x, like so. We're going to get x, like so, and then we're going to multiply this x by each and every term in this polynomial here. So and then we're going to write our result here. So this should give us x to the power 3, and then this should give us plus x squared, and then here we should get plus x, and then here of course we can say plus 0, and then we're going to subtract these two polynomials. Now when we subtract here, we're going to get 0, and then here when we subtract, we're going to get minus x squared, like so. We're going to get minus x squared, and then here when we subtract 2x minus x is going to be plus 2, and then minus 3 minus 0 is going to be minus 3. Now the idea is that we're going to continue dividing until we find a polynomial whose degree is going to be strictly less than the degree of the divisor. The degree of the divisor. In this case, the degree has to be strictly less than 2. Now here we found a polynomial whose degree is equal to 2, and so equal to the degree of the divisor. So we continue dividing, right? So we'll get this first term again and divide it by the first term here. So what we're going to get our minus 1 here, like so. So we're going to get minus 1, right? So that is what we're going to have here. Now here we're going to multiply this minus 1 by each and every term here. So that should give us x squared here, right? Now this is going to give us minus 1. So this is going to give us minus x squared, sorry, because we have minus 1. Minus 1 multiplied by x squared is going to be minus x squared. Then here we're going to, now here we are remaining with an x. We are supposed to have x here because 2x minus, right? We have 2x minus x. Now here we have to, verify that everything is okay before we start writing. So when we subtract, here is x to the power 3 minus x to the power 3 is going to be 0. Now this x squared, now this minus x squared minus x squared here is going to be minus 2x squared, right? So we catch the error here. So 2x minus x is going to be plus x, like so, right? We catch the error. And then minus 3 minus 0 is going to be minus 3. And so here we're not supposed to have minus 1. So we had a little problem there, and we have, fixed the problem here, right? And then same, the degree here, we will continue dividing until we find a polynomial with degree less than the degree of the divisor. But here we have the degree here is 2, and here we have 2. So we continue dividing. So we get our first term, and then we, divide here. So that should give us minus 2 by the first term, that is. So minus 2. Now minus 2 multiplied by that is going to be minus 2x squared. And then this should give us minus 2x, like so. This should give us minus 2x, like so. And then now minus 2, here we have minus 2 multiplied by positive 1 is going to be minus 2. And then here we subtract the two polynomials. Now when we subtract these two polynomials, what do we get? Now here we'll have a plus, so this is going to be 0. Now this is going to be 3x. Now this is going to be a minus 3 plus 2, which is going to be minus 1, like so. Now that looks good. Now this is going to be our remainder. So here we cannot continue dividing because we found a polynomial with degree less than the degree of the divisor. So this is going to be our r of x, and then this is going to be our most precious q of x, like so. And so what do we get here? We get that x to the power 3. Now here I'll write it, at least at the top. So here we're going to get x to the power 3 minus x squared plus 2x minus 3, like so. Is going to be written in the form. So here we have a b multiplied by q. So here our b, which is the divisor, is going to be x squared plus x plus 1, like so. Now that looks okay to me, right? That looks okay. We have x squared plus x and then plus 1, like so. And then here multiplied by what? Now multiplied by the quotient, which is x minus 2. So here we're going to have x minus 2, like so. We're going to have x minus 2, like so. And then plus the remainder, which is 3x minus 1. Now what we're going to do here, I'm just going to get rid of this part here. I'm just going to get rid of this Euclidean division that we have here. Then I'm going to make this a little bit bigger, right? I'm going to make this a little bit bigger. So what did we have? We had 3x minus 1 and then x minus 2. So we're going to get rid of that. Okay. So here we have multiplied by x minus 2. And then here we have plus 3x minus 1. Now to match our denominator here, we're going to divide throughout by x squared plus x plus 1 squared by this highest power. We will now get this denominator, we'll divide it throughout. Now if we divide the denominator throughout here, what are we going to get? So here we're going to have, now this is, we're going to have x squared plus x plus 1 squared, like so. And then same thing here, we're going to divide by x squared plus x and then plus 1 and then squared, like so. And then we do the same thing here. We're going to have x squared plus x plus 1 squared, like so. Now this is our f1. So here we get that our f1 is going to be equal to, now this simplifies with this. So here we should get x minus 2. Then this is going to be divided by x squared plus x, divided by x squared plus x plus 1 squared, like so, plus 1. Now this we're just going to have to the power 1 because we've simplified there, right? Now we can just get rid of the entire expression and rewrite. We have x squared plus x plus 1. Now this is to the power 1. Now that is going to be okay. Then here we're going to have 3x minus 1 and divided by x squared plus x plus 1 squared. Boom. So this is going to be our result. Now this is going to be the decomposition of f. right? This is what we normally get. So we have, you know, a certain, because this is a quadratic expression here, so we'll have a certain alpha x multiplied plus, you know, a certain alpha 2, and then we do the same thing here, and then this is the format that we basically have. But look at how fast that was. Look at how quickly we've gotten, you know, our result here. So this is because we've applied the Euclidean algorithm. We've used, you know, a technique here. So this is the magic. The magic here is that we have applied the Euclidean algorithm to get, you know, quickly to our result. So we're going to, you know, reason in the same way and try to solve the second, you know, and try to decompose the second rational fraction. Now this is, you know, the furthest we can go in R, because we know that x squared plus x plus 1 is irreducible in R. So we're just going to leave it the way it is. So that is, you know, the decomposition for our most precious rational fraction f1. So we get the second one. Now here what we have to do is Euclidean division of the polynomial x squared by x squared plus 2x plus 2. So now here we're just going to write, we're going to call this f2. We're just going to call this f2. Now you can call it anything you want. Now this is going to be f2. Now this is going to be x squared, and then divided by, here we have x squared plus 2x, and then plus 2, like so, to the power 5, like so. That is what we have. Now here we have to, you know, rely on our friend, now the Euclidean algorithm. Now here we're going to say x squared is going to be divided by, now the divisor here is going to be x squared plus 2x plus 2. We basically take it to its smallest power. The smallest the power can be is 1 here, because it is to the power 5. So this is what we do here. Now here what do we have? So here we divide the first term by the first term. Now that is going to give us a 1 here. Now 1 multiplied by each and every term here is going to give us x squared plus 2x plus 2, like so. Now this is 0x plus 0. And then what we're going to do is that we're going to subtract these two expressions. Now here when we subtract x squared minus x squared, we'll get 0. Now here we'll get 0x minus 2x is going to be minus 2x, like so. Now 0 minus 2 is going to be minus 2, like so. Now the idea is that we want to continue dividing until we find a polynomial that has degree strictly less than the degree of the divisor. Now here we've arrived at that polynomial, so we cannot continue dividing. And so this is going to be our R of x, and then this is going to be our Q of x. And so we get that x squared can be written in the form. So here we have x squared plus 2x, and then plus 2, like so, and then plus, and then here we multiplied by the quotient, sorry, which is 1. So we can basically skip the 1. And then because 1 multiplied by x squared plus 2x plus 2 is x squared plus 2x plus 2. So here we're going to have our remainder, which is going to be minus 2x minus 2. And just like before, we're just going to divide by x squared plus 2x plus 2 raised to the power 5, because this is going to be different from 0. So in R, we're going to we're going to be safe, because we're never going to get, you know, division by 0, right? So just like I did in the previous video, we're going to get rid of, you know, our Euclidean algorithm here. And then here what we're going to do is that we're going to divide throughout here by x squared by x squared plus 2x plus 2 raised to the power 5. Now this is going to be x squared divided by, now this is equal to x squared plus 2x plus 2. Now when we divide here on the left, we're going to get f2. So we're going to say f2 is going to be equal to, now here when we divide here, we're going to, you know, simplify here. So here we're going to have 1 divided by x squared plus 2x plus 2 raised to the power 4, because we've simplified there. And then we're going to have plus minus 2x minus 2, like so, and then divided by x squared plus 2x plus 2 raised to the power 5. Now look at, this is normally the format that we have here. It is, we keep increasing in power here, which means here we have 0 divided by x squared plus 2x plus 2 raised to the power 3, and then we also have 0 divided by x squared. The other terms here that are supposed to be here are all equal to 0. That is why we get this result. Now here, if you are to apply the the traditional methods and the traditional techniques here, those that we've used in the previous videos, it is going to take years to get to the answer, right? Now, thank you guys for watching, and I'll see you in the next video.